In this lesson, we are going to cover the last topic of the Chemistry 12 class and look a little bit more about applications of chemistry and how we can apply our knowledge from Chemistry 12. So in this section, we're going to look at 6.5 and talk about electrolytic cells. So a little bit different than electrochemical cells. We're going to describe the structure and function of the electrolytic cell, predict voltage required to operate an electrolytic cell. So that's a little bit different than the voltage coming off of or generated by an electrochemical cell. We're going to compare and contrast the two types of cells. And then we're going to look at three different types of electrolytic cells that are a little bit vary in their complexity. So type 1, 2, and 3. And then finally, we're going to look at a little bit about applications of these electrolytic cells, including electroplating and electrorefining. And I'll include some videos that explain a little bit more about those two processes as well. So first off, when we talk about electrolysis and electrolytic cells, this time what we're doing is we're taking electrical energy and we're converting it to chemical energy. So we're actually running an electrical current through an electrolyte solution and forcing a reaction to take place that wouldn't happen otherwise. So this is transferring our electrical energy into chemical energy, which is the opposite of what an electrochemical cell does. If you take a look at the standard reduction table, when we were looking at spontaneous reactions, we were looking at something where the oxidizing agent was higher than the reducing agent on the chart. When we do an electrolysis, we're going the opposite way around, where our oxidizing agent is lower than the reducing agent on the chart, and we have a non-spontaneous reaction. So here's an example right here where we're taking sodium chloride, common table salt, and we're breaking it down into its ions. So we're going to break it down into sodium ions and chloride ions. So the first question here is this a redox reaction and how can we tell? Well, to tackle that question, the first thing that we're going to do is assign oxidation numbers to everything in that reaction. So if you take a look here, all elements on their own have an oxidation number of 0. So that means the sodium on its own is 0, chlorine on its own is 0. Now in the compound, however, sodium has an oxidation number of +1 and chlorine has an oxidation number of 1. So is this a redox reaction? Well, yes, it is. It's a redox reaction because the sodium is gaining an electron and the chlorine is losing an electron. So there we have an oxidation and a reduction taking place. Is the reaction spontaneous and how can we tell? So for this one, we actually have to go to the standard reduction. If we take a look at the standard reduction table, you can see that the chloride ion going to chlorine gas is taking place from right to left. And sodium going to solid sodium is going from left to right. Now you can see with these reactions, we've got one taking place. Our reducing agent is higher on the chart than our oxidizing agent. So this is a non-spontaneous reaction. So the oxidizing agent is lower than the reducing agent on the chart. That tells us that our reaction is spontaneous. Now, finally, what voltage must you apply to make this reaction occur? If we take a look at what the reactions are, to get sodium to go to solid sodium form, that's negative 2.71 volts. The chlorine going the opposite direction on the chart, we're going to reverse the sign and we're going to add them together. So E naught for the cell is negative 4.07 volts. And to report this, we have to say that we must apply a voltage of at least 4.07 volts to make that reaction occur. The negative sign just tells us that it's non-spontaneous and that we have to put power into this to make the reaction occur. So how do we form an electrolytic cell? That's the next question. To build an electrolytic cell, it's actually easier than an electrochemical cell. We can do it all in one. So if we take a beaker here, and we put in 2 electrodes, 2 different types of metal, and we're going to attach them to a DC source. So the cathode is where the reduction reaction is going to take place. Anode is where the oxidation reaction is going to take place. And we do this all within an electrolyte solution. We hook this up to a DC source, so a direct current. And with our DC source, our electrons are going to be flowing from the right to the left-hand side, from anode to cathode, just like they were in an electrochemical cell. And that's basically all there is to setting up an electrolytic cell. When we want to determine voltage required and look at the overpotential effect, we have to keep in mind that spontaneous reactions occur in reverse of spontaneous reactions. Reaction nearer to the top of the SRP chart is going to read from right to left, and the one nearer the bottom of the chart goes from left to right. So that's opposite to what we saw in our electrochemical cells. To find the voltage required to operate the cell, we're going to just add the oxidation and reduction potentials together. We should get a negative number, and a negative number tells us that we have to put a voltage into that to make it take place. Okay. Now, the other thing that we have to take into account is that because the SRP chart was built on standard conditions and everything was theoretical, the actual voltage required to operate that cell is likely higher than the theoretical value, and that's called the overpotential. The overpotential of water in particular is quite a bit higher, and you'll notice that on the SRP chart, there is kind of a transfer area for overpotential of water because it requires so much more than the theoretical value of water as well. It allows us to do a little bit of extra calculations there. The other thing that you'll note is with electrochemical cells, if we're looking for which reaction is going to take place, we look for the strongest oxidizing agent and the strongest reducing agent. So they're the farthest apart on a chart. With electrolytic cells, we're looking for the minimum voltage required for a reaction to take place. So we're actually looking for the two that are closest together on the chart. So here's an example. We're going to predict the voltage required to operate the electrolytic cell here. So we've got nickel plus 2 electrons leading to solid nickel, and we've got iodine ions leading to I2, elemental iodine, plus 2 electrons. So what we're going to do here to find the voltage required is, first off, we're going to find both of those on the table. So my E naught for the nickel is negative 0.26 volts. That's the one going from left to right. The other one here with the iodide, we're going from right to left, and so we're going to reverse the sign. And so that's going to be negative 0.54. To figure out the voltage required to operate the cell, we're going to add those two together. So I get an E naught of the cell of negative 0.80 volts. And so we have to apply at least, so something greater than 0.80 volts to operate that cell. Here are 3 more practice problems for you to try. See if you can predict the voltage required to operate each of the following electrolytic cells. So please pause the video, try them on your own, and then play the video again to get the correct answers. Okay, for the first question, you'll notice that the silver, we're going to actually have to switch the sign on that one because it's going from right to left. So it's going to be negative 0.80. Oxidizing agent is negative as well, so negative 0.26. So we're just going to add those two together, and we get a total of negative 1.06 volts. So it requires at least 1.06 volts to operate. With the second one, it's the fluoride that's going to be switched with the sign. Copper is actually going to be positive. So the E naught of the cell, when we add those two together, is negative 2.53 volts. So it requires at least 2.53 volts for that reactions to take place. And lastly, we get a total E naught of the cell of negative 1.8 volts. So it requires at least 1.8 volts to get those reactions to take place. One great thing about your workbook here is that there's a chart in here that actually compares electrochemical and electrolytic cells. It makes it easy to see the differences and similarities between the two. You'll notice with electrochemical cells, these are exothermic reactions. These are kind of making electricity. We're taking chemical energy and we're transforming it into electrical energy. With electrolytic, it's the opposite. It's an endothermic reaction that requires energy. So we're transforming that electrical energy from a DC source, so from a battery or a DC power generator, into chemical energy. With electrochemical cells, we need two half cells to do this. So we can either do it in one container with a permeable barrier, or we can do it in two containers and put a salt bridge. With an electrolytic cell, because we're supplying that electron flow, we can do it all in one container. You'll notice that electrolytic are non-spontaneous, whereas electrochemical are spontaneous, and that corresponds to the E0 value. So kind of when you're looking at things, if you're looking at electrochemical reactions, you're looking at the left hand, the oxidizing agent to be higher on the chart than the reducing agent, and electrolytic, it's going to be the opposite. As well, with electrochemical cells, we're looking at the two half reactions that are farthest apart on the SRP table, whereas electrolytic, you're looking for the two closest together, so they require the least possible voltage to drive that cell. So here's a quick check as well. Try and figure out what each of these are, electrochemical, electrolytic, or both, based on the clues. So pause the video and then play it as soon as you would like to get the answers. So first one here, having two half cells, that's an electrochemical cell. With the second one, you're going to actually have to look at your SRP table. And we find that that one is an electrolytic cell. We're kind of going from right down to left, okay? Next one, oxidation occurs at the anode. That is both. Transforming chemical energy into electricity, that's going to be an electrochemical cell. And electrical charge requires a complete path or circuit. That is both as well. So we achieve that with an electrochemical cell in the two containers by using a salt bridge, for example. With number 6, you can use the SRP table to calculate how much voltage it takes to operate me. Technically, this will be an electrolytic cell because it takes voltage to operate it. If it said how much voltage it will generate, that would be electrochemical. And then lastly, with the E0 being positive, that's going to be an electrochemical cell. Now we're going to look at the 3 different types of electrolytic cells. So type 1 cells are the easiest ones to kind of conceptualize. However, they're a little bit difficult to make in real life because they require molten ionic liquids. So we actually have to melt our salt. And so they take place at a very high temperature. With these ones, we use inert electrodes, so either a carbon electrode or a platinum electrode. We put those electrodes into a molten ionic liquid. So in this particular one, we would take our table salt, heat it to about 800 degrees Celsius, so it melts it. And then it's only the molten ions that could be oxidized or reduced. So nothing is actually aqueous. The only 2 possibilities that we have for that reaction to take place is the sodium cation and the chlorine anion. With type 2 cells, now we have inert electrodes, but this time we're doing it in an aqueous ionic solution. So we've got dissolved ions. Now in this case, water can also act as an oxidizing agent or a reducing agent. So we have a cation, an anion, and we have water as either an oxidizing agent or a reducing agent. So what we need to do is find the cation, anion, and water on the chart. And the 2 closest together on the chart, the 2 that require the least amount of voltage, are the ones that will actually react. With type 3 cells, we put one more complication in. Rather than having inert electrodes, we now have non-inert electrodes that could potentially participate in that reaction as well. And as well, we have an aqueous ionic solution. So it just makes one more level of complexity here. So for this one, you can see that the things that we have that may be reacting are the copper electrode. The platinum's not going to react because it's inert. However, we've got an ionic solution. So we have anions and cations in that water that could react, or we also have water that could react. So we have a number of different things that could react together in those type 3 cells. Lastly, in this lesson, we're going to take a look at a couple of applications of these electrolytic cells. So one of them is electroplating, and this is used quite frequently. This is when we take one metal and we deposit it onto another metal. So some inexpensive jewelry makes use of this all the time. If you look at silver collection, like silver spoons and things like that, often we've electroplated silver onto there so that the entire spoon itself doesn't have to be silver, because that would be very expensive. So what we do with this is we deposit one metal onto another metal. So what we do is we flow electricity from a battery onto the cathode, and the cathode becomes negatively charged and attracts ions in that salt solution. So in this particular one, for example, we've got zinc ions in the solution. When we move energy or electrons from the battery onto that cathode, the zinc ions will then come to pick up the electron and deposit themselves onto that cathode. Meanwhile, the anode is replacing the ions. So this anode would be zinc, and as the ions are moving towards the cathode, we continue getting more of those cations from the anode until it's used up. So you can see three examples of electroplating there. There's a regular unplated penny, there's a penny that has been plated in nickel, and then another penny that's been plated in gold. There is also a video that accompanies this that I'll put in the lesson thing to show how electroplating exactly works. A last example that I'm going to give you of electrolysis is electrorefining. And this is used quite frequently in mining to take an impure sample of metal and to purify it. So we might do this to make, say, like gold bars, or to make a solid copper chunk that we can then export, rather than exporting tons of this unrefined stuff. So what we do is we hook up a pure, this one is copper, a pure copper cathode, and this is where all the metal is going to deposit. So it requires a pure sample to begin with. And then we have an impure sample as well. So how we do this is we hook up a battery so that the negative terminal is running into that cathode. The cathode is where the electrons are going to deposit themselves. So those electrons, when they run down that pure copper cathode, what they're doing is they're attracting cations in the aqueous liquid. So the cations continually get refreshed because we have that impure copper anode that keeps dissolving. And the copper, it more readily accepts the electrons than the other elements in there. And so we end up with this kind of anode mud at the bottom, where we get the silver and the gold and the platinum, any of those things that are not as easily attracting the electron as those copper ions are. So we can do this several times, and then also refine the mud as well, because you don't want to lose the silver or the gold or the platinum either. But we can make a very pure sample by doing electrorefining. So again, I'm going to put a video of how this process exactly takes place as well. And I hope you enjoyed learning a little bit about some of the applications of the chemistry, and thanks for watching.